Let us discuss some more examples of aromaticity. We have the cyclic part and we have the structure like this. We have a positive charge on the top and the negative charge at the bottom. In this case, if you talk about here, all the atoms in the cyclic structure are taking part in conjugation. That is, this compound is ring conjugated. The positive charge would mean presence of an empty orbital, while the negative charge on carbon means the presence of the lone pair. And further, we have two pi bonds. So here, the condition being satisfied is empty orbital, single bond, pi bond, single bond, lone pair, single bond, pi bond, single bond, and empty orbital. So this is entire cyclic conjugation. Here, the number of electrons taking part in ring conjugation are 6. The n value turns out to be 1, so this particular compound is cyclic conjugated and aromatic. While we could have the compound, the seven-membered cyclic structure, this is cycloheptatrienyl cation. This particular cycloheptatrienyl cation is also called tropylium ion. This tropylium ion has 6 electrons in cyclic ring conjugation. One carbon has an empty orbital, and so this compound is aromatic. Then we could have a particular peculiar compound. This particular compound is called cyclooctatetraene. The cyclooctatetraene, I have made the structure as a planar compound, but the cyclooctatetraene is actually not planar. This compound is tub-shaped. Tub-shaped would mean that this compound is a non-planar compound. Here, the 8 electrons which are present in the pi bond, they are not in ring conjugation. You might be tempted to say that this compound is anti-aromatic since here M value would turn out to be 2, but the compound is actually non-aromatic and it is actually non-conjugated. So there is no question of this compound being aromatic or anti-aromatic since it's already non-conjugated. This is cyclooctatetraene. Then we could have a compound like this. This compound is 10-annuline. Annulenes are the compound which contain alternate pi bond in a cyclic structure. This 10-annuline has overall 10 electrons, which should be cyclic conjugated, and this compound should turn out to be aromatic. But this compound has a peculiar problem, and that peculiar problem is that in this particular compound, the two hydrogens on the carbon facing towards each other are pointing towards each other. Due to the steric hindrance or physical repulsion between the two hydrogens, this structure actually becomes non-planar. And when the structure becomes non-planar, it becomes non-conjugated and it is not aromatic. Now, if we take the same structure and instead of being having the two hydrogens pointing towards each other, if we take the compound and instead of hydrogen here, we have a carbon attached here, like this is the CH2 group here. Now the CH2 group would push the two carbons towards each other, and now this particular compound becomes aromatic. This is aromatic. Then we could have some other structures, like we have a famous compound called naphthalene. In naphthalene, we have all the atoms taking part in cyclic structure to be providing exactly one orbital towards conjugation. So this compound is cyclic conjugated. This compound has 10 electrons in cyclic conjugation. That means the n value turns out to be 2 and this compound is aromatic. Similarly, we have another compound. This compound is what we know as azulene. Azulene has again 5 pi bonds and it has 10 electrons in cyclic conjugation. In fact, the two rings tend to be a kind of fused ring of cyclopentadienyl anion and cycloheptatrienyl cation. So here, what we find is that this ring tends to have a positive charge while the smaller ring tends to have the negative charge, which makes the compound highly polar. It has the charge separation making the compound highly polar. Then we could have another compound. Now, this particular compound is what we know as 14 aniline. This is 14 aniline. Here again, we have 7 pi bonds. There are 14 pi electrons. The value of N would turn out to be 3, and this compound is aromatic. Then we could have a compound like 16 aniline. This compound 16 aniline has 16 pi bonds having 16 pi electrons. It has 8 pi bonds, which makes the value of M to be 4, and this compound would be anti-aromatic. It's not a compulsion that we have to have only one or two rings. We could have even more rings. We could have something like anthracene. Anthracene has 3 benzene ring fused with it, and this compound is aromatic. There are so many aromatic compounds. Now, till now, we have talked about the aromatic compounds which were containing only carbon in the cyclic structure. The aromaticity is, or anti-aromaticity for that matter, or conjugation for that matter, is not the property of carbon. It is the property of conditions. We could have some other atoms also which could be aromatic. Like we have something called furan. Furan is aromatic. Here, the oxygen contains two lone pairs, but out of these two lone pairs, only one lone pair has a capacity to take part in the conjugation. An atom can contribute only one orbital towards conjugation, so oxygen also is able to contribute only one lone pair out of the two, and the compound becomes aromatic. Here, the number of electrons taking part in ring conjugation is 6. Similarly, we have pyrrole. Pyrrole again is aromatic. Nitrogen contributes the lone pair. Then we have thiophene. Thiophene has sulfur. Again, it contributes one electron pair. Then we have something like pyridine. Pyridine has nitrogen with the lone pair, but the electron pair of nitrogen does not take part in conjugation. There are 3 pi bonds which contribute the electron towards ring conjugation. The 6 electrons are there in ring conjugation, which makes pyridine aromatic. Then there is a peculiar example in which we have 0 carbons. We have BH, we have NH, NH, BH, BH, and NH. If we talk about this particular compound, this compound is called borazole, borazine, or inorganic benzene. This compound has the condition of empty orbital single bond and the lone pair repeated over, which makes it cyclic conjugated. The number of electrons taking part in cyclic conjugation is 6, provided by 3 nitrogens, lone pair, and this compound is aromatic. That is why it is termed as inorganic benzene. Then there are certain compounds which are not exactly aromatic per se in themselves, but they do become aromatic by breaking of bonds. Something like we have a structure which is called tropone. Tropone has double bonded oxygen. Now, this double bonded oxygen, the bond breaks, wherein giving the positive charge to the ring and oxygen gets the negative charge. When the ring gets the positive charge, it becomes aromatic. So here, this tropone is actually aromatic due to the cleaving of the bond. In the same manner, there could be a compound like we have a cyclopentadienyl ring, and we have a cycloheptatrienyl ring joined together by a pi bond. Now, this bond actually cleaves towards the cyclopentadienyl ring, creating a negative charge on the cyclopentadienyl ring, while the positive charge on the cycloheptatrienyl ring and creating the cation. Now, this makes both the rings aromatic and the compound becomes aromatic. So, this is what we have as some cases of aromaticity, wherein we have the heterocyclic rings, we have the homocyclic rings, and we have the examples where the aromaticity or conjugation even is blocked due to the steric factors or the structure.